A historic idea, so far ahead of its time that even today we're not ready for it. Not because we don't understand it, but because of what it demands. A spacecraft powered by nuclear explosions, designed to reach Mars in days. Not a theory, not science fiction. This was real, seriously studied by scientists in the 1960s. A spacecraft that by almost every measurable metric was better than anything we fly today. More powerful, faster, bigger payload. We had the blueprints, we had the physics, we had the engineers. But we cancelled it. Most people remember one thing about Project Orion, that it could reach Mars in just 10 days. But nobody ever asks the harder questions. How does the spacecraft work? How safe is it for the astronauts? And why not get vaporized in the process? That's what this video answers, and the engineering is even more insane than the idea. Forget everything you know about rockets for a second. Project Orion doesn't have an engine the way you'd normally think of one. No fuel tanks, no combustion chamber, no slow burn, no nozzle, no propellant tank. At the back of the spacecraft sits a massive metal plate, thick, heavy, circular. This is called the pusher plate. It's the most important component in the entire design. I am sure it will blow your mind when you understand how exactly the sequence works. A small package called a pulse unit is ejected from the rear of the spacecraft. It drifts roughly 50 to 100 meters away. Then it detonates. The explosion releases a superheated ball of plasma expanding outward at enormous speed. The pusher plate is directly in that plasma's path. The plate absorbs the hit, gets pushed forward, hard. That force travels through a system of giant shock absorbers connecting the plate to the rest of the spacecraft. By the time the impulse reaches the crew module, the sharp explosive jolt has been converted into a sustained, manageable push, like a heavy elevator accelerating upward. Then it happens again, 1 second later. Another pulse unit, another detonation, another push. The original designs called for roughly 1 explosion per second, each releasing around 0.15 kilotons of energy. Small by nuclear standards, but in space, even a small device delivers a staggering amount of thrust. To reach orbit, the engineers calculated it would take approximately 800 individual pulses, 800 nuclear detonations in roughly 13 minutes. That's not a rocket, that's something else entirely. So the immediate question that comes to our mind hearing this is, how does a spacecraft survive hundreds of nuclear explosions detonating meters behind it? That's the magical discovery of Project Orion, which seems physically impossible. The answer comes down to 3 things: distance, design, and the physics of space itself. First, distance. In space, there's no air to carry a shock wave. On Earth, a nuclear explosion destroys buildings not just from heat, but from the pressure wave moving through the atmosphere. In space, that doesn't happen. The energy travels outward as plasma and radiation, with nothing to amplify it. The destructive radius drops significantly, and the pulse units detonate far enough behind the plate that the plasma hits the plate, not the spacecraft body. Second, the pusher plate itself. It isn't just raw steel. The original designs called for a thick ablative coating, a layer of graphite oil that vaporizes on contact with the plasma, carrying heat away. This is the same principle used on re-entry capsules, controlled sacrifice of the surface to protect what's underneath. Third, the shock absorbers. Between the pusher plate and the spacecraft body sits a 2-stage dampening system. First, large pneumatic pistons absorb the initial impact. Second, a secondary spring system smooths out what remains. Think of it this way: you can punch a thick mattress as hard as you want. The other side barely moves. The engineering challenge was never whether this could work. The physics confirmed it could. The challenge was building components that could survive 800 cycles of this without failure. Now let's talk about what this propulsion system actually produces, because this chapter is where Project Orion stops being a thought experiment and starts being genuinely unbelievable. Engineers measure rocket efficiency using something called specific impulse. Think of it like fuel economy for spacecraft. How far can you go per unit of propellant burned? The best chemical rockets ever built, the engines on the space shuttle, score around 450 seconds. And Project Orion? 2000 to 10,000 seconds. Not twice as good, not 3 times, up to 22 times more efficient. But efficiency is only half the story. The Saturn V, the rocket that sent humans to the moon, could carry 130 tons to low Earth orbit. Still one of the greatest engineering achievements in history. An Orion spacecraft could carry thousands of tons. Some designs on paper called for spacecraft the size of ocean liners because the propulsion could support it. Imagine launching a spacecraft the size of a cruise ship into orbit, not because the engineers were being reckless, because the math said it was possible. And then there's the speed. A conventional rocket burns its fuel and maxes out at around 7 kilometers per second. After that, it coasts. Orion doesn't coast. It keeps detonating every second as long as it has pulse units. At full theoretical performance, Orion could reach 3 to 10% of the speed of light. I know that sounds too good to be true. So why does such a revolutionary invention, which were also being tested successfully, was never being used in real missions yet? The physics was confirmed, the engineering was understood, the blueprints existed, a working prototype had already been tested, not in a computer simulation, in the actual desert. And then comes the most frustrating part. In 1963, the United States, the Soviet Union, and the UK signed the Partial Nuclear Test Ban Treaty. No nuclear detonations in the atmosphere, no detonations in space, no detonations underwater. Every single condition of early Project Orion designs violated. Launching Orion from the ground meant detonating 800 nuclear devices inside Earth's atmosphere. The fallout? The engineers calculated it. They said roughly 10 cancer deaths per mission across the global population. They argued it was an acceptable trade-off for what the technology unlocked. The world said no. Freeman Dyson, one of the physicists who actually worked on Project Orion in its prime, later called it the greatest missed opportunity in the history of astronautics. Not something said for a documentary, his actual, sincere assessment. The project was cancelled in 1965, classified, shelved, quietly buried, and humanity went back to chemical rockets. The same fundamental technology we still use today. Now here is a big question for you all. Why can't we use this technology without causing any harm to humanity? Hear me out. The 1963 treaty is still active, which violates the use of nuclear power. That's still the legal wall. But here's what nobody told you. Orion doesn't have to launch from Earth. What if you built it in orbit? A conventional rocket lifts the components up, piece by piece. Engineers assemble the spacecraft in space, far above the atmosphere. The first pulse unit fires only after you're completely clear of Earth. No fallout, no atmospheric contamination, no population at risk. The original objection, gone. But the engineering obstacles, real, but not insurmountable. Material science today is decades ahead of 1965. Precision manufacturing, radiation shielding, computer-controlled pulse timing, all of it has advanced dramatically. And the concept didn't die with Project Orion. In the 1970s, British scientists proposed Project Daedalus, an interstellar spacecraft using controlled fusion pulses instead of fission bombs. Even cleaner, even more powerful, and still physically valid today. So what's actually in the way? Not the science. The science has been settled for 60 years. Not the engineering. The engineering problems are solvable. It's political will. It's treaty restructuring. It's the word nuclear in the description. Humanity is not being held back from the outer solar system by physics. We're being held back by paperwork.